In this video, we're going to start abstract algebra, and we're going to talk about algebras and operations. So this is going to be very difficult to grasp at first if you're a linguist first and foremost, and you're not really exposed to mathematics, but I'll do my best to make sure everything is as intuitive and clear as possible, so that way if you go further in semantics or in other areas of mathematical linguistics, you're able to grasp these concepts and utilize them in your own systems. So first of all, an algebra A, which I'll always write kind of cursively, is a set A together with operations f1, f2, all the way up to fn. So we could write something like the algebra A is the ordered pair or ordered n-tuple A, f1, f2, all the way up to fn. And there could be one operation f1, or there could be n operations f1 through fn. Here's something that is a little bit more familiar. So the algebra A consisting of the real numbers, addition, and multiplication. So we're used to things like, oh, 3 plus 2 is equal to 5. So that's an operation in the real numbers. We also have multiplication. So 3 times 2 is equal to 6. There's another case of multiplication with the real numbers, so this is an algebra, and we're very familiar with this notion. We've also encountered some other algebras so far, such as propositional logic, as well as some other things which we'll talk about later in the video. So algebras have to satisfy two axioms, which is essentially a requirement to be an algebra. We don't need to prove these properties about our systems, they're just requirements. So I'm going to say that the algebra A consists of a set A and an operation, which I'll just call circle. So this is a general operator. We don't know what this is. This could be addition, this could be multiplication, it could be something like union for sets, it could be the AND operation for logic, it could be anything. This is just general. We're being very abstract here. And the first axiom is closure. And this says, for any two elements in A, there is some C that when you take two elements and use the operation on it, you get C, and all those elements are in the set. So essentially, if I take two things in A, I use an operation on them, I better get something else that is also in A. So the first example is the real numbers and addition. So essentially what I'm saying here is, okay, let's say I take the numbers 3 and 2, and I add them together with the operation. Well, I know 3 is a real number, I know 2 is a real number, and when I add them together, I better also get a real number. And in fact, in mathematics, when you have real numbers in addition, you always get another real number. So if I take 3 plus 2, I get 5. 5 is a real number. Therefore, this system, or this algebra with the real numbers in addition, is closed. So we could say the real numbers are closed under addition. But what if I just take the integers less than or equal to 0 and multiplication? Well, what happens there? Well, if I do a nice example, let's say if I do 0 multiplied by -1, I just get 0 back. So 0 is an integer less than or equal to 0, -1 is an integer less than or equal to 0, and then its output is 0, which is also an integer less than or equal to 0. So that's a good example. However, what if I multiply two negative numbers together? What if I take -1 times -1? Well, -1 is an integer less than or equal to 0. Therefore, if this is an algebra, my output better also be an integer less than or equal to 0. However, -1 times -1 is 1, and 1 is not an integer less than or equal to 0. Therefore, this algebra, in quotes, algebra, consisting of integers less than or equal to 0 and multiplication, does not satisfy closure. Therefore, this isn't actually an algebra. So, if we're introduced with, say, an ordered pair with some set and some operation, in order to check to see if it's an algebra, we have to make sure that there's no counterexamples. In this case, there is a counterexample. If we take -1 times -1, this third element C, its output, is not in our original set. Therefore, this isn't going to be an algebra. The second axiom is uniqueness. And that states that if A is equal to A prime and B is equal to B prime, then if I do an operation on A and B, it better be equal to the operation on A prime and B prime. And I'm going to introduce this with the integers modulo 4. So essentially, we can think of this as the remainder divided when dividing by 4. So for instance, if I have the number 7 modulo 4, then, well, what is 7 divided by 4? 7 divided by 4 is equal to 1 remainder 3. So we can say 7 modulo 4 is equivalent to 3 modulo 4. So I know this is kind of math coming out of nowhere, but it's a good example here. So for instance, I know 7 essentially is equivalent to 3. So I can say, okay, so 7 is equal to 3. And as another example, let's say if I take 5 modulo 4, this is equivalent to, well, 5 divided by 4 is going to be 1 remainder 1. So this is equivalent to 1 modulo 4. So as 7 equals 3, 5 equals 1. So if I do 7 plus 5, this better be equal to 3 plus 1. So 7 plus 5 is 12. I should write mod 4 here just so the math people don't get mad at me. But so 12 mod 4 should be equivalent to 4 mod 4. And is this true? Well, 12 divided by 4 is 3 remainder 0. And 4 divided by 4 is 1 remainder 0. So yes, this is the case. It satisfies uniqueness. Okay, so there's a math example. I kind of want to step away from this. But the point is, every algebra must obey those two axioms. The first one is closure, the second one is uniqueness. So now, let's look at some algebras we know. For instance, we know the algebra consisting of the real numbers addition and multiplication. And we can verify these properties if we want. So if we take some real number a and we multiply it by another real number b, then we're going to get another real number, whatever that is. Similarly, if we add a plus b, we'll get another real number. We also have to check uniqueness. So, for instance, if I have a equals a prime and b equals b prime, then a times b is going to equal a prime times b prime. And I don't really want to verify this right now. It's a lot of meaningless nonsense to linguists anyway. So maybe we can go to b, which is something more familiar. So we have a set containing S, which we'll just call atomic sentences or statements, negation, conjunction, disjunction, and the conditional. And this is another algebra. So for instance, if I start with P and I do an operation on it, like I take the negation of P, this is also still in S. And what if I take two elements, P, Q, and I use conjunction with them? Again, this is also in our set of proper statements in logic. So this is another algebra. The third one, C, is essentially the semantics, so truth values. So for instance, if I take 1 in conjunction with 1, I get 1 out of it. If I take 1 in conjunction with 0, I get 0 out of it. So no matter what, we're going to end up with something in 0 and 1. So those are some examples of algebras we've already dealt with. And you might be thinking first, whoa, these propositional logic and predicate logic are algebras? Yeah, so this is abstract algebra. This isn't just the stuff you do in high school. It's more formal, it's more abstract. So much like the real numbers with addition and multiplication is an algebra, so is propositional logic, and so is the semantics of propositional logic. In fact, I'm sure you can think of even more algebras, which I'd be interested if you put them in the comments below. Maybe some other algebras you've encountered while you're at school or maybe on your own studies. So that's algebras. Now I want to talk about operations. And I'm always going to use the circle as an operation. It's just a general operation. And operations can have different properties depending on the operation itself. So we can say an operation is associative if for every A, B, and C in some set A, if we do A, B first and then C, it's the same thing as doing B and C first and then A. So in other words, the way that we group them essentially doesn't change the output. So for instance, One you're already familiar with is multiplication. So if I do 3 times 2 times 1, this is the same thing as doing 3 and then multiplying 2 times 1 together first instead. So if I did 3 times 2 first, I end up with 6 times 1. On the other side, if I do 2 times 1 first, I end up with 2. So this will be 6 times 1 is equal to 3 times 2. And indeed, they are the same. So multiplication is associative in the real numbers and integers. So that's associativity. We've seen this before in propositional logic and set theory. Commutativity says that, well, an operation is commutative if for every a and b, the order doesn't matter. So a circle b is equal to b circle a. So again, if we have 3 times 2, this is equal to 2 times 3. What if we have set theory? So if I want to do a intersection b, we know that's the same thing as b intersection a. So we can say that the intersection operation is commutative. What about the difference operation? So a minus b. Is that equal to b minus a? No, they're not the same. They give us different sets, and we can check that with Venn diagrams or with the definition. So the difference operator is not commutative. Okay, the third one, idempotent. So an operation is idempotent if for every a, if we use the operation on itself, we just get itself back. So one example of an idempotent operation is the intersection. So if I do a intersection a, I get a back. Similarly, if I do a union a, I get a back. So we can say that intersection and union are idempotent. However, what about multiplication? So if I do 3 times 3, do I get 3 back? No, I don't. I get 9 back. So multiplication under the real numbers and integers would not be idempotent. So those are 3 properties. We do have one more. So the fourth one is distributivity, but this requires 2 operations. So we can say for 2 operations, circle 1 and circle 2, we say that operation 1 distributes over operation 2. If for every ABC, if we do A, then operation 1 with B, operation 2, C, we get A operation 1B, operation 2, A operation 1C. And this is a bunch of garbled nonsense if I just show you these operations, so let's give you a nice concrete example. So let's say I have 3, and I want to multiply that by 2 plus 3. What I'm saying here is then that would be equivalent to 3 times 2 plus 3 times 3. And is that true? So let's just check. Well, 3 times 2 plus 3 is just 3 times 5, which is equal to 15. Well, 3 times 2. Well, 3 times 2 is 6. And then I add together 3 times 3, which is 9, which is also equal to 15. So yes, this is true. So we can say that multiplication distributes over addition. But does the other way around work? So let's ask ourselves that. What if we switch these operations around? So what if I take 3 plus 2 times 3? Is that equal to 3 plus 2 times 3 plus 3? So this would be 3 plus 6. Is that equal to 5 times 6? And the answer, of course, is no. 9 is not equal to 30. So addition is not distributive over multiplication. What are some other examples we've seen before? Well, if I recall, if we have A intersection B union C, this is just equal to A intersection B union A intersection C. And we've seen this before, so we can say that intersection is distributive over union. And similarly, if we do A union B intersection C, this is also just equivalent to A union B intersection A union C. So in this case, union is distributive over intersection. So we have operation 1 distributive over operation 2, and operation 2 is distributive over operation 1. Okay, so those are the 4 different properties of operations. Now let's check 3 of them as an example before we end this video. Here's the first one. Let's take a look at the integers with addition. First of all, is it associative? What does that mean? If I add 3 plus 2 and then 1, is that the same thing as adding 2 plus 1 first and then 3? And the answer is yes. So it is associative. And we could check every single example in the world if we want to, but we know enough about addition and integers to know that this is true. What about commutativity? Or commutativity? Is 3 plus 2 equal to 2 plus 3? If we pick any 2 elements, is that the same? The answer is yes. Is it idempotent? Well, if I take 0 plus 0, I get 0 back. So that looks good, right? But I can find a counterexample. If I take 1 plus 1, I get 2. And that's not okay to be idempotent. We want this to be equal to 1. So this is not equal to 1. Therefore, no, it's not idempotent. So the algebra consisting of the integers and addition is associative and commutative, but not idempotent. What about the universe and intersection? So is it associative with intersection? Well, if I take A intersection B intersection C, this is equivalent to A intersection and then first B intersection C. So yeah, for any 3 sets, intersection is associative. Commutative, yeah, we know that A intersection B is equal to B intersection A for any 2 sets. And idempotency, well, A intersection A is of course going to equal the set A. So yes, it is idempotent. The third one is probably the one you haven't considered before. And in fact, when I take a look at textbooks to figure out examples for these, it's one I never ever see as an example. But I think it's really good to think about operations in this sense. So I have truth values 0 and 1 and the conditional. First of all, is it associative? So if I have 0, arrow 1, arrow 0, where we do 0, arrow 1 first, is that equivalent to doing 0 but having 1, arrow 0 first? So let's check to see if it's associative. So 0, arrow 1 is 1, so on the left side we end up with 1, arrow 0. And on the right side we have 0, and then we have 1, arrow 0 on the right, and we know that's false, so it's 0. So is 1, arrow 0 equal to 0, arrow 0? Well, 1, arrow 0 is 0, 0, arrow 0 is 1. These are not the same. So conditional on truth values is not associative. Is it commutative? So is 1, arrow 0 equal to 0, arrow 1? The answer is no, because 1, arrow 0 is 0, and 0, arrow 1 is 1. Therefore, it is not commutative. Okay, it's not associative, it's not commutative. Maybe it's idempotent. Let's cross our fingers. Let's check. Okay, is 0, arrow 0, does that give us 0? No, it gives us 1. So no, that's not good. So it is not idempotent either. And I think that's a really good example just to show that we shouldn't assume that every system we use is associative or commutative, or for the most part, idempotency. We don't assume it's idempotent ever, but usually associativity and commutativity, we're like, yeah, I think that's a common property. But some cases, such as the conditional in propositional predicate logic, it's not quite easy. It's not just obviously associative or commutative. In fact, it's not at all. So if you have any questions about this stuff, please leave your comments down below, and I'll answer them the best that I can.